All right, everyone, get ready, because today we're diving deep into something that's like the bedrock of, well, everything around us.
Yeah.
Literally.
We're talking about the fascinating world of chemical bonds.
These invisible forces are running the show, holding atoms together to create every single substance we see and touch and even breathe.
You might be thinking, bonds. That sounds a bit, dry and technical, but trust me on this one.
It's anything but dry.
Once you get a handle on these interactions, the way you see the world, it totally transforms. Like you're putting on a new pair of glasses.
Totally agree. And for this deep dive, our trusty guide is chemicalbonding.pdf.
A document absolutely packed with details.
Bursting at the seams, really. But don't worry.
That's why we're here to pull out those golden nuggets of information.
The aha moments. The stuff that makes you appreciate just how cool chemistry can be.
Exactly.
Okay, picture this. You've got a diamond, right? Known for its incredible strength, can withstand crazy pressure. Then you've got a lump of coal, which, well, crumbles pretty easily.
Or think about this. Why can you dissolve salt in water, but not sand?
These might seem like simple everyday things, but it all boils down to the different types of chemical bonds that are at work.
And chemicalbonding.pdf breaks down these bonds into three main categories: ionic, metallic, and covalent.
Each with its own quirks and characteristics, and they have a huge impact on the properties of materials.
Good time.
Let's kick things off with ionic bonding. This one always reminds me of a kind of, turbulent love affair in the atomic world.
Huh.
We're talking about atoms with drastically different levels of electronegativity. Basically, electronegativity is how strongly an atom attracts electrons to itself.
Like, imagine a giant game of tug-of-war, but one team is way, way stronger than the other.
Okay, so not exactly a fair fight for those electrons then, is it?
No, not really a fair fight. The stronger atom, the one with the higher electronegativity, it basically ends up snatching an electron away from the weaker atom.
Electron robbery.
Pretty much.
So what does this electron exchange do to the atoms themselves?
Well, it transforms them into what we call ions. The electron thief, the one that gains an electron, it becomes negatively charged. That's what we call an anion. And the atom that loses its electron, well, now it has a positive charge. That makes it a cation.
Makes sense. So we've got these charged particles, quotients, and anions just hanging out now.
Not exactly hanging out. In chemistry, opposites attract, right? So these positive and negative ions, they have this strong electrostatic attraction to each other. And that attraction is what forms the ionic bond.
So it's not just a fleeting thing. This is a powerful bond that creates a very specific structure.
Exactly. It's a highly ordered three-dimensional structure called a lattice.
And this lattice structure is key, right? It's not just a random jumble of ions.
Definitely not. Our source, chemicalbonding.pdf, brings up table salt or sodium chloride, NaCl, as a classic example of ionic bonding.
Makes sense. We use salt every day.
Exactly. So sodium, it has this one lonely valence electron in its outer shell. And chlorine, it's got 7 valence electrons, so it really wants one more to complete its outer shell and be more stable.
And stable makes atoms happy.
You got it. So sodium, being generous, readily donates its electron to chlorine. This turns sodium into a positive ion, M+, and chlorine into a negative ion, Cl.
And then, boom, they form that ionic bond.
Exactly. And those ions arrange themselves in a repeating cubic lattice structure.
Like a perfectly organized little world. So this lattice structure, how does that explain why ionic compounds like salt are typically solid at room temperature?
Good question. It's all about those strong attractions, that tightly packed arrangement of ions. It creates strong attractive forces in every direction. Think of it like a really well-built Jenga tower, but instead of wooden blocks, you've got these charged ions locked in this tight embrace.
Okay, I can visualize that.
To melt an ionic compound, you need to pump in enough energy to overcome those strong electrostatic forces that are holding the entire lattice together. And that's why ionic compounds often have pretty high melting points.
So it's like trying to rip apart that super strong Jenga tower. Takes some serious force. But what about other properties of ionic compounds? Our source mentions brittleness, for example.
Right, and that brittleness also comes down to the lattice structure. If you apply enough force to an ionic compound, you might end up shifting the alignment of those ions, and suddenly those positive ions might find themselves right next to other positive ions. Same with the negatives.
And what happens when you try to force, charges together? They repel each other, like trying to force the same poles of two magnets together.
Exactly. That repulsion, it can actually cause the whole lattice to split apart, which explains why ionic compounds can be brittle.
Makes sense. So that's ionic bonding in a nutshell. Electron theft, strong attractions, and this really organized lattice structure. But what about metals? Our source, chemicalbonding.pdf, makes it sound like they have a totally different approach to bonding.
They do. Metals are all about sharing. They're like the ultimate sharers of the periodic table.
Okay, so less of a tug-of-war over electrons and more like everyone just chips in and shares.
Exactly. Picture this. A sea of electrons.
A sea of electrons.
Yeah. These electrons, they're not bound to any one specific atom. They're delocalized, which means they're free to roam around the entire metallic structure.
So instead of being stuck with one atom, they're just kind of floating around.
Well, not exactly floating. I mean, they're still attracted to those positively charged metal ions, the atoms that have contributed their outer electrons to this shared pool. But the key here is that they're not confined. They can move around freely throughout this whole lattice of metal ions.
And chemicalbonding.pdf points to this sea of electrons as the reason why metals are such incredible conductors of electricity.
Right. It's like this. When you apply a voltage across a metal wire, those mobile electrons, they don't really put up a fight, they just flow, carrying that electrical current along with them.
Which makes sense. Electrons on the move, electricity. But in ionic compounds, those electrons are kind of stuck in that rigid lattice, right? So they're not exactly good conductors when they're in their solid state.
Exactly. And this electron freedom, it also explains why metals tend to be so malleable and ductile.
Meaning we can hammer them flat, stretch them out into wires, all that good stuff. You try doing that with an ionic compound, it'll probably shatter.
Exactly. The metal ions, they can just slide past each other without breaking up that overall structure. Think of it like a mosh pit at a concert, you know? Everyone's moving around, bumping into each other, but the crowd as a whole, it stays together.
Okay, I like that analogy, a mosh pit of electrons. But here's a question that's been bugging me. If it's all about this sea of electrons, how come different metals have such wildly different melting points?
Ah, that's a great question. And our source, chemicalbonding.pdf, it actually addresses this. It all comes down to the strength of the attraction between those metal ions and that electron sea.
Okay, so the stronger the attraction, the harder it is to pull those ions apart and melt the metal.
Exactly. And the strength of that attraction is influenced by something called ionization energy.
Ionization energy, right. That rings a bell. Remind me what that is again.
Basically, ionization energy is a measure of how much energy you need to rip an electron away from an atom. The higher the ionization energy, the more that atom is clinging to its electrons. Like, these are mine.
Get your own electrons.
Exactly.
So if a metal has a high ionization energy, it's going to hold onto those electrons in the sea more tightly, making it harder to melt, right?
You got it. It's like trying to pry something out of someone's hand when they have a super strong grip. Good luck with that.
Let's look at a real-life example. Tungsten. You know, the metal they use in those old-fashioned incandescent light bulbs?
Yeah.
Tungsten has a really high ionization energy, which makes sense because those filaments in the light bulbs, they have to get insanely hot to emit light.
Exactly. Now, on the flip side, think about mercury. It's a liquid at room temperature.
Wow, that's a big difference.
Right. And that's because mercury has a pretty low ionization energy. The attraction between its ions and that electron sea is weaker, which means it has a much lower melting point.
Okay, so from those workhorse tungsten light bulbs to the more free-flowing mercury, it seems like the strength of that metallic bond really dictates a metal's properties.
It's true.
Fascinating. But let's switch gears a bit because chemicalbonding.pdf still has a lot to tell us about that third major type of bonding, covalent bonding. All right, so we've explored the world of ionic bonds with all that drama of electron transfers.
And those communal electrons living it up in the metallic bonds?
Right. Now we're moving on to covalent bonds. It sounds like atoms are entering into a more, committed relationship with this type of bonding.
I like that analogy. Covalent bonding is all about sharing electron pairs to create a more stable arrangement. It's like a partnership where each atom brings something to the table to make things work.
Okay, I can see that. But I have a feeling that electron negativity is going to make a comeback in this story. Remember how we talked about how it can lead to unequal sharing?
You know it. Chemicalbonding.pdf really emphasizes that point. Remember our tug-of-war analogy from before?
Yeah, with the strong atom versus the weak atom.
Right. Well, in covalent bonds, it's more like two equally matched teams pulling on that rope. If the two atoms involved have very similar electronegativity, they're going to share those electrons pretty evenly. That's what we call a nonpolar covalent bond.
So it's a balanced partnership. But what if one atom is a little bit, let's say, greedier than the other? Like it has just slightly higher electronegativity.
That's when we get into polar covalent bonds. Imagine you're sharing a really delicious dessert with someone. Even if you're both technically sharing, one of you might be enjoying it just a tad more than the other.
I think I know someone like that.
Haha, exactly. So when it comes to atoms, this uneven sharing, it creates what we call partial charges.
Well, partial charges.
Right. Instead of having full-blown positive and negative ions like we saw with ionic compounds, we end up with regions within the molecule that are just slightly positive and slightly negative.
Ah, okay. So it's not a complete separation of charge, just a little bit of a shift.
Exactly. And our source brings up water as a perfect example of this.
Oh yeah, water, the molecule that makes life on Earth possible.
Right. And it's all thanks to those partial charges.
So how does it work in water?
Well, oxygen, it has a higher electronegativity than hydrogen, right? So in a water molecule, H2O, the oxygen atom pulls those shared electrons a bit closer to itself, creating a slightly negative region around the oxygen.
Okay, I'm following. So what about the hydrogen atoms?
Since those electrons are being pulled away from them, they end up with those slightly positive regions. It's this polarity, this difference in charge distribution that makes water such a good solvent.
A good solvent. You mean that's why water can dissolve so many things?
Exactly. Those partially positive hydrogen atoms in a water molecule,
Yeah.
they're attracted to negatively charged ions or the slightly negative regions of other polar molecules. And the oxygen end of a water molecule can interact with positively charged things.
So it's like those partial charges act like little magnets, attracting other molecules and pulling them apart.
That's a great way to put it. And because of this, water can dissolve a huge variety of substances, from salts to sugars.
Wow. It's amazing how these tiny little charges can have such a massive impact. But what about the strength of covalent bonds? Does the distance between the atoms matter at all?
Absolutely. Chemicalbonding.pdf talks about this important relationship between bond length, which is just the distance between the nuclei of two atoms that are bonded together, and bond strength. And you know what? It's an inverse relationship.
Inverse. So does that mean shorter bonds tend to be stronger?
You got it. Imagine two people holding hands. The closer they are, the stronger their grip is. Our source gives a few examples. The hydrogenite bond, like you find in a hydrogen molecule, is really, really short, and it's a very strong bond. But if you compare that to the chlorine ClCl bond.
Let's see, chlorine is a bigger atom, right?
Right. So that ClCl bond is longer, which means it's a weaker bond than the HH bond. You don't need as much energy to break it apart.
Interesting. So we've got bond polarity with those partial charges and everything, and we've got bond strength, both of which are affected by how electronegative the atoms are. Covalent bonding is more nuanced than I thought.
It really is, and it doesn't stop there. We've been talking about individual bonds, but these bonds can link up to create a mind-blowing diversity of molecules.
Yeah, it's not like covalent bonds just form these simple little structures and call it a day.
Not at all. Chemicalbonding.pdf makes it very clear that covalent bonds are like the master architects of the molecular world.
Okay, I like that. Master architects.
They can create everything from small, straightforward molecules like carbon dioxide, CO2.
Right, the stuff we breathe out.
Exactly. To these giant, crazy, complicated network solids like diamond, which is famous for being incredibly strong and durable.
And speaking of visualizing these intricate structures, can we talk about Lewis structures for a minute? They kind of sound like an art technique rather than something you'd use in chemistry.
Haha. I can see why you'd say that, but trust me, Lewis structures are incredibly useful for getting a clear picture of how electrons are arranged within a molecule.
Okay, so it's like a map of those electrons, showing us who's sharing with whom.
You got it. And our source really emphasizes how important the octet rule is in covalent bonding. See, most atoms, they're really striving for a full outer shell of 8 electrons.
8? Why 8?
Well, 8 electrons in that outer shell, that represents a super stable electron configuration. And for atoms, stability is key. It's what they're always aiming for.
So it's like that quest for a full outer shell is what's driving all this sharing and bonding in the first place.
Exactly. And Lewis structures, they help us visualize how those electrons are being shared to reach that magic number 8. Let's take methane, CH4, as a quick example. It's a pretty simple molecule.
Okay, methane. So carbon, if I remember correctly, has 4 valence electrons.
You got it. So it needs 4 more electrons to get to that stable octet. And each hydrogen atom, it has 1 valence electron, so it needs 1 more.
Okay, so how does it all work out?
Well, carbon, it's like the friendly neighbor who's willing to share. It can form 4 single bonds, one with each of those 4 hydrogen atoms. By sharing, everyone wins. Carbon gets its full outer shell, and so do the hydrogen atoms. Everyone's stable.
That's really elegant. It's like each atom finds the perfect partners to fill in those electron gaps. But wait a minute, our source mentioned that there are exceptions to this octet rule, right? It seems like in chemistry, there's always an exception to the rule.
Haha, that's true. Just like with any rule, there are always a few rebels who like to break it. Some atoms, especially those in the third period of the periodic table and beyond, can actually handle more than 8 electrons in their outer shell.
Really? How is that possible? I thought 8 was the limit.
Well, it turns out that these atoms can tap into what are called their d orbitals. They're like extra rooms in the atom that can hold more electrons. And that gives us something called expanded octets.
Expanded octets, okay. So more than 8 is possible. And are there any other exceptions to the octet rule?
There are a few. For example, there are some molecules out there like boron trifluoride, BF3. In this case, the central boron atom actually ends up with fewer than 8 electrons, but it's still stable.
Chemistry is full of surprises. So we've got exceptions where atoms have more than 8 electrons, exceptions where they have less than 8. But what happens if there's more than one way to actually draw a Lewis structure for a molecule? How do we know which one is right?
That's a great question. And that's where we get into the world of resonance. Chemicalbonding.pdf describes it as a way to show what's happening when you've got a molecule or an ion where a single Lewis structure just can't quite capture the full picture.
So it's like the molecule is saying, hey, I can't be confined to just one arrangement of electrons. I like to mix things up a bit.
That's a great way to put it. It's not that the molecule is rapidly switching back and forth between different structures, though. Instead, the real structure of that molecule or ion, it's like an average, a hybrid of all those different resonance structures.
Okay, I get it. It's more like a blend of possibilities rather than one static picture.
Exactly. And those electrons that are involved in resonance, they're what we call delocalized, which means they're not stuck between just 2 atoms. They're spread out over more than 2 atoms.
Wow. So we've gone from these basic electrostatic interactions that hold ions together to all these different ways that electrons can be shared in covalent bonds. It's amazing how much diversity there is at the molecular level.
It really is. And what's incredible is that everything we've talked about today, it's all happening at a scale that's way too small to see with our naked eye.
It's true. But even though we can't see these bonds directly, we experience their effects everywhere we look.
Absolutely.
Whether it's the incredible strength of that diamond in your jewelry, the conductivity of the copper wires that power our homes, or even the life-giving properties of water, it all boils down to those invisible forces of chemical bonding that are holding atoms together, creating the world around us.
It all starts with those bonds.
It really does. And on that note, we're going to wrap things up for today. But before we go, we'll leave you with a final thought-provoking question courtesy of our trusty source, chemicalbonding.pdf. Knowing that many substances don't fit neatly into just one category of bonding, what do you think the properties of a substance with a mix of both ionic and covalent character would be like?
It's something to ponder.
It is. Keep those brain cells buzzing, stay curious, and we'll see you next time for another deep dive into the fascinating world of science.